Lecture 18. Coming down the home stretch. Last call for feedback. Does anybody have any of those forms they wanted to turn in related to the sale manager's feedback? Lab Thursday, we'll continue on with rations. You'll do your first ones. Reading and analysis sheet, we'll start review sessions next week. Rest of the semester, this is your chance to vote. So exam 2 will be either Monday, November 8th or Wednesday, November 10th. Do you have a preference? How many people like the 10th? 8th? Okay. Feed ID exam, Thursday or Wednesday, November 17th or Monday, the 22nd. How many people would like the 17th? How many people would like the 22nd? Those of you on the 22nd, is there any reason you couldn't do the 17th? Just prefer not to.
I like the weekend.
Okay, so we'll work on that one. Probably be the 17th, but we'll figure that out one way or another. Final exam will be during finals week. I think it's posted, but I haven't got to it yet. So everybody signed up for Costers? We're set for this week. So letters. Which is an essential amino acid? Alanine, lysine, glycine, or proline? The answer is lysine, number B. So lysine is usually the one we run into limits on first. Those of you who watched the Jurassic Park movies, that's the supposed control that they put on the animals. I kind of giggled when they said that, but anyway. Which is an essential amino acid, tyrosine, serine, glutamine, or threonine? So D is what we're looking for, threonine. So our list here of essential ones, threonine is up there with lysine. Non-essentials. So just for my own edification, which thing might you be using to memorize your essential amino acids? Which of those things I offered, or are you going to do something else original on your own? Okay, pretty good mix. So what I want to talk about right now is the fates of protein. We already alluded to this already. Okay, we'll go that way. So we have, as we mentioned already, the challenge of feeding protein to cows is the rumen. And what I want to present to you here today is a system I came up with to help you learn this. It's not going to be anywhere available outside of this class, but I think it's the best way to learn it. Just from an understanding standpoint, as you get out in the real world, everybody's got their own letters for their own system, and we'll allude to those as we go forward. So, we've got the rumen. Definitely not working. We've got our rumen bugs. So representing a significant volume of the rumen. We will have 4 fractions that behave differently, distinctly inside the body. So we'll have A, B, C, and D. These are nitrogen-containing fractions, and we'll get into the details of those. What happens where? Then we have the small intestine, omasum, abomasum, small intestines. What we're interested in is what gets to the small intestines. That's what the cow has to work with. So we're going to divide these up into 2 categories. The A and B fractions and the C and D fractions. The C and D fractions are rumen inert. They kind of go into the rumen. They wander around for a while. Nothing happens to them. They go to the abomasum, small intestines. C and D fractions are unchanged by the animal or by the microbes. So as they come in, that's what ends up at the small intestine. The A and B fractions are going to be very much influenced by the rumen microbes. They might become part of the microbes, the protein that makes up their bodies. They might get chewed on, fall out, and they'll be altered in some way, or they might be completely destroyed in some way, shape, or form, ripped down to nothing. So the A and B fractions are going to become microbial protein. That gets to the small intestines. The protein is broken down into individual amino acids, and those individual amino acids are absorbed. The C and D fractions are going to be our feed protein that is available to the animal, and that is only going to be the C fraction. So only the C. The D fraction is nitrogen-containing compounds that are unavailable to the animal. We can think of them as plastic. They're going to go in the rumen, be untouched. They're going to go in the intestines, be untouched, pass right through the animal. These will occur, certain natural compounds in the plants will do that, but you also have things that happen when we put up feed badly. We talk about heat-damaged feeds, either hay or silages, where the protein reacts with the carbohydrate to make that plastic. So that D is going to go beyond the intestine, pass right through the body unchanged. So your animal's going to make her living off of whatever is created by the microbes from the A and B fractions and the C fraction. Everybody with me so far? Okay, let's get into some more details related to these fractions. So you have this handout here where we're going to go through and describe in detail what's in each of these fractions. So the first thing we'll talk about is sort of what's there. The A fraction is going to be things that contain nitrogen but are not actual protein. We're going to call that NPN, non-protein nitrogen. So that's anything that's not a long chain of amino acids that has nitrogen in it.
What was the sugar content?
So we're waiting for it to come back up here. So again, this is a system I came up with for this class. So NPN, non-protein nitrogen. So we don't have real protein in the A fraction, but it does contain nitrogen. B is going to be the nitrogen that's used by the bacteria, and this is going to be actual protein. So non-protein nitrogen and protein that is available to the microbes, either by solubility, by availability, by spatial, physical limitations. It's the amino acids, the protein that are available to that animal. And they can be used by the microbes in the rumen. We've got C fraction is nitrogen that is not used by the microbes in the rumen, and this is also protein. So we've got non-protein nitrogen, protein, protein, and then for D, it's not going to be available to either the cow or the nitrogen. It's unavailable nitrogen. It's a plastic of some sort. So depending on the character of that protein, depending on the properties of that protein, we're going to have different fates of that protein entering the rumen. Our NPN is generally what we call, last time we talked about soluble protein. Little small molecules that go into solution very easily in the rumen, and the microbes have direct, easy access to them. when we're figuring out what's in these two fractions, we're going to do it by difference. What goes into the rumen, what comes out of the rumen. And our last one we'll measure directly by doing a Kjeldahl nitrogen on our ADF. When the feeds are damaged, that nitrogen ends up in the cell wall fraction attached to the cellulose. A cross linkage between lysine and our cellulose happens, forms a plastic that is unavailable to the microbes in the rumen, unavailable to the cow. This might be available to fungi, but fungi grow very slow over long periods of time. So they have the time and patience to work through that, to break that apart. So more details on what's in that A fraction. We've already mentioned urea. 2 ammonias stuck to a carbon. We sometimes feed this to ruminants to give them a little bit of extra in the rumen. But it's not in any way, shape, or form organic nitrogen at this point. We may have that nitrogen in the form of single amino acids floating around. This happens a lot in the haylage as it ferments. The proteins get ripped apart and the amino acids go into solution. We may have small peptides. We can think of a peptide as up to 10 amino acids in a row, strung together. But we're focusing more on the 2 and 3 and 4 chain amino acids. We also will have vitamins. There are certain vitamins that have nitrogen in their structure. They will also fall into this category. Nitrates, nitrites will also fall in there as well. So you're thinking about very small, readily available to the microbe, useful to the microbe things there. So they're in solution. As we mentioned already, the B fraction is true protein, thousands and thousands of amino acids struck together. And these are proteins that the microbes can reach. So you have things that are in solution, proteins that are in solution, proteins that are toward the surface, proteins that become very, very much soluble for those microbes so they can get in touch with them. So non-protein nitrogen, protein nitrogen are the two things that the microbes have to work with and grow and multiply, live, party, and die. Going through. Our C fraction is true protein that the microbes, for whatever reason in the rumen, are unable to touch. They can't reach it. It's too far inside the feed. It's surrounded by a coat of some sort. It's not soluble. So if it's not soluble, the microbes can't see it. But once that protein gets to the abomasum, hit with acid, starting that digestion of protein, continuing on into the small intestine, those amino acids are freed and the cow can absorb them. And as we said before, that unavailable nitrogen, you've got lignin. There's a lot of nitrogen in lignin, but that is not available to the cow. We may have bound protein that through our preservation process, we've heated up that protein, got it to like 160 degrees, and you get that hay that smells like burnt tobacco, or that silage that smells like caramel. Has anybody experienced that? So if you're putting up silage too dry or you're putting up hay too wet, you might run into these. So the protein, particularly the amino acid lysine, cross-links with other things, and you get that polymerization reaction, and we create plastic, in effect, that passes through the cow, untouched by the microbes, untouched by the cow. Everybody with me so far? Does that make sense? So this is not how the real world divides things up, but this helps you get conceptually a start on this. So what we're going to do now, and you might want to take out a new sheet of paper, is I'm going to draw how these fractions lay out. So as with the slide up there, if you get a clean sheet of paper, if you need paper, give a holler. Turn it sideways and probably fit better. So kind of setting things up. We've got a bar here that's going to represent all the intake, all the protein consumed by that cow. So in the NRC, you'll hear that called intake protein. Intake crude protein, or all the nitrogen that is consumed by the animal. We could also, in this class, call it the eaten protein, what goes into the cow. And then what we'll do is we'll break that bar up into different categories, into different systems that you'll see out in the world. So this is my system for this class. They are equal in the sense that it's just easier to draw. They are not equal in real life. This is highly variable. It could be up to half. This tends to be very small. So we had the A, which contains that non-protein nitrogen. We've got our B and C fractions that have the real protein, the true protein that exists or the animal consumes. And then you have the bound or unavailable protein in the D fraction. If we look at those fractions, as we've said before, the A and B are available to the microbes. So available to the microbes is this portion of there. In most feeds, it might be 1/2 to 2/3. What's available to the cow is A, B, and C. If the microbes don't take that true protein for some reason, the cow can take it. Or anything up in the A fraction could be absorbed by the cow. Ammonia or urea is not going to be helpful to the cow immediately, but any of those amino acids would, any of those peptides would. Cow can use them, but usually the microbe gets to them before the cow does. So that's the challenge with balancing protein for a cow, is what happens in the rumen and trying to figure that out. So we've mentioned soluble protein. That is going to be called formally SIP, S-I-P, soluble intake protein. The crude is implied in there. And that's going to be all of our A fraction and a little tiny bit of our B fraction. There's a certain amount of true protein that goes into solution. That, as we said, will be very available to the microbes. They're going to destroy it, they're going to use it, they're going to repurpose it very, very quickly. So SIP is the formal thing that's used in the NRC, soluble intake protein. So we've got SIP, we've got DIP, we've got YIP moving forward. So if you really get into this, you can spend a lifetime trying to study all this stuff. After SIP, we're going to have two different categories of protein or nitrogen, crude protein or nitrogen. Rumen altered nitrogen. So we've already said that the microbes are available to that. So that is our A and B fractions, rumen altered nitrogen. And then we have the rumen inert, the protein, the nitrogen, the crude protein that is unchanged by the animal or by the microbes in the forestomach. So rumen inert, just like we talked about fat, we also have rumen inert crude protein. The formal names for these two different fractions are degraded and undegraded. Trying to separate it from digested, making the cows in charge. But that rumen altered will also be called degraded nitrogen, degraded crude protein. The stuff that remains untouched in the rumen is called undegraded crude protein or undegraded nitrogen. It used to be called bypass. It bypasses the rumen, yes.
You take either answer.
Yeah, I don't care. What I'm trying to do is teach you the vocabulary. That's the purpose of this class, to teach you the vocabulary. We might abbreviate those as RUP and RIT. Rumen undegradable or undegraded protein, rumen degraded protein. So again, we're doing the A and B versus the C and D. So this is the spelling out there. We've got the RDP, ruminal degraded or degradable protein. So depending on you're going into the rumen or you're coming out. So graded coming out, degradable going in. RUP, ruminal undegraded coming out or undegradable potentially going in protein. So it's interesting, they're supposedly bringing out a new NRC, first one in 20 years, this December. I'm interested to see where they go with all the feeds and all the animal stuff. You'll also hear it, depending on the system you are in. And this goes back to our intake protein, our soluble intake protein. Undegraded intake protein is C and D. Degradable intake protein is A and B. So degradable or degraded intake protein, undegradable, undegraded intake protein. So degradation is a reference to what the microbes do. Although on their level they're doing a digestion, but we're trying to separate digestion by the cow from the actions of the microbes. So we're calling that degraded or undegraded. Everybody with me so far? Does that make sense? So depending on whose school you go to, you might have different emphasis, different nomenclature. There is a base system, and it'll be interesting to see if this sticks in the NRC or if they propose something new. We have the NRC, National Research Council recommendations on dairy cattle. We have the CNCPS, Cornell Net Carbohydrate Protein System, or the CPM, Cornell Penn Minor Protein System. And they basically balance out, instead of having 3 letters involved, they have only, or 4 letters involved, they only have 3. So you have the A fraction, roughly equivalent in that system to the SIP, soluble intake protein. And then you have 3 B fractions, A1 or B1, B2, and B3, that all have different rates associated with them. B1, very quickly available to the microbes, B2 slower, B3 the slowest available to the microbes. And then there's the C fraction that's roughly equal to my D fraction. So what happens in the NRC, the CNCPS, or the Cornell Net or Penn Minor program, is that in each of these B fractions, you have a certain amount that is affected by the microbes and a certain amount that is not. So we probably should have did this a little bit different, but most of this B1 is altered by the microbes. We could say half of B2 is affected by the microbes, maybe only a third or a quarter of B3 is affected by the microbes. So within each B fraction, we have my B and C fractions. So I probably should redraw that because not all that is available. So NRC, National Research Council, CNCPS, Cornell Net Carbohydrate Protein System, which was the first version to come through. NRC was probably next. Cornell Penn Minor was probably the last one to come through, but there's a lot of overlap in the nomenclature, a lot of overlap in the theory or the description of the mechanisms that happen. So everybody following what's there, everybody comfortable with that description? You ready to be tested on it? Well, we're going to do it anyway, just for giggles. Okay, getting out your letters again. What happens to Dr. Mooney's A fraction of the crude protein in the rumen? A, nothing. B, converted from protein to amino acids, becomes part of the microbe's protein. D, takes a right at the reticulum, a left at the cranial pillar. So C is what we're looking for. So it becomes, in an ideal world, all of that non-protein nitrogen is soaked up and turned into microbial protein. That is our competitive advantage as a ruminant. So A fraction available to the microbes, part of the degraded, altered fractions. What happens to Dr. Mooney's D fraction of crude protein in the rumen? Same choices. So So nothing converted to amino acids becomes part of microbial protein. Takes it right at the reticulum, the left at the cranial pillar. A is what we're looking for. So D goes in there, wanders around, leaves the same configuration, same chemistry as when it went in. So our D fraction unavailable to both the microbes and the cow, passes through the cow unchanged. B fraction, what happens to that? So we have true protein entering the rumen in the B fraction. And B or C would probably be a legitimate answer. It's certainly going to take that protein, possibly rearrange it, possibly use it direct. It might break it down, might make it part of the protein, might just alter it, let it pass on through. So that B fraction is available to the microbes, which should be eventually available to the cow. C fraction, what happens in the rumen to the C fraction? Take a chance. C fraction, what do we know about the C fraction? A, nothing happens to it in the rumen by definition. So Dr. Mooney's C fraction, C and D, nothing happened. They enter the rumen, they leave the same chemical configuration. So nothing happens to either of those fractions. We assume that the A and B are going to become part of the microbes, making things a little simplistic in this class, but what we need. So what two sources does the cow get her essential amino acids from? So we're going back to our drawing. Microbial protein, which was A and B, and the C fraction. The feed protein that is in the rumen, untouched, going through, but comes out the other side and available to the animal. So we're talking about the need of amino acids to the small intestine. Microbes can make their own amino acids. Cows have a limited ability to do so. They prefer stealing pre-made from other sources, plant microbes. So we need those amino acids when we're feeding a cow to the small intestine. So whatever goes in the rumen, we have the fermentation. What comes out is what the cow has to make a living on. So BFAs, microbial protein, undigested feed, which would contain that C fraction, undigested protein within that undigested feed. It'll have undigested starch, undigested NDF. Those gases are of no use to the cattle. So if we're thinking about our requirements, as we mentioned before, at the small intestine, she needs all of those amino acids to be provided at the small intestines. But with the rumen, we can get away from having them required in the diet. You can feed a cow a non-protein diet and still get milk protein produced because of what the microbes will do in the rumen. You could feed her a little bit of urea and newspaper, or just any paper for that matter that has cellulose in it. And those microbes will say, okay, non-protein nitrogen, an A fraction, I can turn that into amino acids so I can grow. Those amino acids become the sole amino acid source for the animal since there was a protein-free diet. So you need a nitrogen source and fiber for those microbes to create the amino acids. Will you get maximum production feeding a cow urea and newspaper? No, but it can be done. Taking those low quality inputs, the microbes lift them up, and we get something greater at the small intestines the cow can work with. So fed is different than what's needed at the small intestines. And the microbes are the black box, the unknown, the wild card and all that. Does everybody follow that? Does that make sense at this point? So where does a cow get her two sources? She's going to live off that microbial protein, which is a dairy cow, probably about half, maybe more, maybe less. Half of her protein comes from the microbes that she digests. And then whatever feed protein gets from the mouth all the way to the small intestines without being altered by the microbes. So microbial protein was the A and B fractions of the system I proposed to you. And this can be up to half, possibly on a cow out on pasture, not doing much else. It might be 3/4 of the protein that she uses to live. So feed protein is that C fraction. And conversely, it's anywhere from 1/4 to half of what she consumes or has available in the amino acid, as amino acids in the small intestine. Everybody getting that this is a complicated thing associated with our cows? But if we can learn to take advantage of it, we can create protein, which is the most expensive ingredient we buy, except for maybe minerals. The more microbial protein we can create, the lower we can get our feed costs, the cheaper we can produce milk, the longer we might stay in business. So taking advantage of that rumen in some way, shape, or form, using its competitive advantage, gives us a chance. So save this sheet for next time. I have a quiz for you. So when you're done with your quiz, you can quietly drop it off in the front and be on your way.